Hello, everyone, and welcome to the CFD Dose podcast. Today, we're kicking off our very first episode with a very special guest, Dr. Jeff Franklin, a true pioneer in the CFD/CAE industry. Jeff's incredible journey began back in 1991, when, as a graduate assistant, he worked on a groundbreaking project with a software package that you might recognize today with the name ANSYS Fluent. This early experience set him on a path to tackling real-world engineering challenges using computational methods. Jeff's passion for innovation was clear from the start when structured meshing limitations actually became a barrier to his work. He didn't just adapt, but he developed his own CFD tool, creating a finite element program that is capable of solving fluid flow problems and real world problems using unstructured grids. This drive for pushing boundaries has shaped Jeff's career for over 3 decades now. And since 1993, he's been with the Airflow Sciences Corporation, solving countless industrial problems with CFD. But his contributions didn't stop there. Jeff's personal passion for CAE software development led to the creation of Azure CFD, we know today, which is a very industrial and very powerful tool for industry from a CFD perspective that has been making waves for over a decade now. With degrees in mechanical and chemical engineering, a PhD in mechanical engineering, and a professional engineering license in Michigan, Jeff brings an unparalleled depth of expertise and CFD experience to the table. And today I'm thrilled to have him on the podcast today to share some of his insights on the evolution of finite volume methods and the correlation of that approach to collocated grids, and also talk a bit about the impact of his work on the engineering landscape. Without further ado, I'm excited to introduce to you our guest today, and let's jump right into it. Right, thanks very much, Jeff, for coming on our podcast and being the first respected guest of the CFD Dose podcast. Today we will talk about the control volume approach and the correlation with the collocated CFD tools. Jeff, the floor is yours. Thank you.
Thanks, Mo, and thanks for having me. It's an honor to be the very first. It's exciting. I'm looking forward to seeing the people that you get to talk on these different topics. Of course, this is a topic, CFD techniques are something that I really enjoy discussing and learning about, and letting others know a little bit about maybe what I have learned along the way as I learned about CFD. So today, I'd like to talk a little bit about the control volume approach, just from a general engineering perspective, and try to relate that control volume approach to the collocated CFD tools that are commonly used today. Just a little bit of background. Azure CFD is one of the CFD tools that I have developed over the years, which can be found down here if you want to know more information about it at azurecfd.com. So let's start this discussion. So the overview of this discussion I'd like to do is just I want to talk about the control volume approach. And first of all, I'd like to really talk about what is it, how does it relate to the collocated methods that we use, and then we're going to look at a simple example, a very simple example of how we can use the control volume technique for the conservation of mass. And once we kind of have a little bit better understanding of that, then we're going to take that understanding and we're going to look at how collocated data relates to that from a mesh topology standpoint. And then maybe we'll go and do a little bit of a review of the history, because all numerical algorithms that we use regularly kind of has a history. It has a series of steps. We learn something, it works well, and then we want to make it better, so we do something different. And there's, a lot of technology evolves like that, and CFD algorithms are no different than that. And then I'd like to end with just a little bit of a discussion about surface integrals, because CFD tools, we use those for engineering purposes, and so we maybe have something very complex that we're studying using our CFD tools, and we want to be able to get engineering information out of the CFD tool, precise information, rather than just colors. I mean, colors are good, they give us a good understanding, but sometimes surface integrals gives us the engineering information that we need, and the surface integrals allow us to get this very precise information. And so we'll do that. We'll kind of look at that, and then we'll look at a simple example based on conservation of energy. So that's kind of the overview of what I'd like to cover in this discussion. So let's just start with what is a control volume, and anybody who may have been in the engineering sciences or physics or things like that, you've probably done a homework problem of some sort where you basically build a box of some sort, and you look at stuff going in and out of that box or forces around that box or something like that. And that is the control volume that you build. And here I'm just going to look at the conservation of mass, for instance. And so we kind of have a box here. It's a volume, and we have some mass flowing in on one side of the box and it's leaving on the other. And there's some inherent things that we know about that just based on conservation of mass. For instance, if the mass coming in and out is constant, then the volume and the mass inside the volume is constant. But if the mass going in and out is not constant, then either the volume has to change, your control volume, or the mass inside the box needs to change. And those are just some fundamental aspects. We do that for energy, kinetic energy. We do it for a lot of different types of transport fields, but that's basically keeping track of stuff going in and out of our control volume. So now let's look at a little bit more complicated control volume. Here I have a control volume. We have our box, and we have some sort of slotted system. So we have a fluid, since we're kind of talking about CFD tools, a fluid is entering the slot here. It's passing through this slotted system, and then it exits here. And we kind of know a little bit of information about mass flow. Mass flow over here is kind of a combination of the density of the fluid, perhaps the velocity of the fluid right here, and the area. So we know a lot of these things, and typically we know a lot about our geometry, and we know a lot about our density of our fluid, but the velocity is oftentimes what we're really interested in doing. And in particular, we can, based on conservation of mass, we can figure out perhaps what the velocity is at this location, or perhaps at this location. But with our CFD tools, we want to know a little bit more information about what's inside our box. What perhaps might be the velocity at this location. And this is what our CFD tools allow us to do, is to kind of peer inside a portion of the system that we are interested in looking at and determine what, in this case, what the velocity might be at this location. And we can use our control volume techniques to kind of break down this larger system control volume into smaller ones that we can then get use this type of relationship to speculate what the velocity would be at maybe an internal location that represents, these basic fundamental conservation of mass in this particular system. So that's kind of what we're going to look at. And so for CFD tools, just in general, the cells themselves can be complicated. They can be simple things like a hexahedral or a tetrahedron, but these days it's very popular to even use polyhedral cells, where it's kind of shown over on the right-hand side. And this is usually kind of a fixed grid. So the grid is kind of in one location for many CFD applications. You do have some applications where the grid itself might move, but for most CFD applications that are done, the grid is in one fixed location and the fluid kind of flows through the grid. And we can integrate it, and the CFD tool typically has one value at the middle of each cell that says this is kind of the mean value that kind of represents kind of locally in this area what the fluid properties are, its velocity, temperature, whatever it may be. And then we have on each one of these surfaces typically a CFD tool just because of ease, has some sort of planar surface. And a whole bunch of these planar surfaces combined together kind of bound our control volume, and that represents, our control volume in general. It's kind of enclosed by these planar surfaces. And then to kind of keep track of what goes in and out, we kind of pick a mean value, and that's these little blue dots right here, about what is going in and out of this system, just like we talked about with that square at the beginning of this discussion. So now we have a mean value that's going in here or out. Like here, the mean value would be kind of some sort of average value of these two green vectors right here that would represent what's leaving. And here we would have these two vectors, and what this blue dot would be kind of a mean value of those. So those allow us to find out what's going in and out. Well, there's kind of one other aspect here, are these normal vectors. Just like with any other engineering problem, you kind of have to pick a kind of some sort of convention about what is in and out. And mesh topologies have that in them, where you have this normal vector that is kind of based on the topology of your mesh. And this normal vector says which way your convention is, and then you use that along with these vectors. So like you can see that this vector, this normal vector, is opposite to what maybe the fluid path line is. So in order to find out the flow volume in here, you would maybe use this normal vector, maybe dotted with this actual fluid vector right here. So this is how the control volumes in our CFD tool kind of exist, and we collect these together. And this has all of the same properties we would assume. And we can conserve quantities such as momentum, mass, and energy in each one of these control volumes. For steady state, so we're just going to kind of take a look at a steady state control volume. So now let's look at just a simple control volume system here, and we're going to look at the conservation of mass. So we have a system control volume, which is kind of this gray block right here, and then we kind of have this nozzle geometry. And what we have is so the flow is going to come in, it's going to kind of get forced through. This is our system right here, which is kind of composed of 3 different cells or control volumes in here. And what we really want to try to do is we want to kind of peer in here and find what's going on inside this system. If we are just simply given a mass flow rate on this side, can we really kind of speculate what the value of, say, for instance, of the fluid velocity would be in each one of these control volumes, these sub-control volumes? So we really want to kind of calculate the fluid velocities at these locations 1, 2, 3, 4, and 5 using conservation of mass. We're going to assume kind of for this example, steady flow conditions, we're going to make the density constant, and we're going to say our known value is a specified mass flow rate right here on the left-hand side of this. So we're going to use conservation of mass to find velocities at these locations, and these velocities are going to be a velocity profile that represents conservation of mass. So we're doing conservation of mass, and it's one thing to make sure we understand is there's no such thing as conservation of velocity. There is conservation of mass, and there is a velocity field that represents conservation of mass, but there's no conservation equation for velocity alone. What we're looking for is velocities at these locations that conserves mass. So how do we go about doing that? Well, I guess we need a little bit of information here if we're going to kind of keep track of what's going on in each one of these cells, because we want to know, well, right here, we kind of know what's going in, or the mass, what is going in on this location 1, but what about on this face right here? How do we determine what kind of, what is the representation of the velocity so we can find the mass flow rate as it leaves this first cell? And so we're going to base this representation on some sort of generic interpolation technique. And there are many interpolation techniques that you can use to figure out what a value might be at this location. And so we're just going to kind of generalize it in this particular case. And we're going to say, we're just going to use the velocity, this v2, which would be our self-centered velocity on the left-hand side of this face, and v3 on the right-hand side, and just some weighting value on either side. And we'll say we'll pick a weighting value of 2 plus a weighting value of 3. And this weighting value is between 2 and 3, so it has a descriptor of 2, 3. And then we can sum those up between the two of those, and we can say, well, this is kind of a representative velocity based on our interpolation assumptions about what the velocity would be right on this face. And we can do a similar thing between control volume 3 and 4 right here. So now we have kind of a representation of the velocity, so we can kind of characterize the mass flow rate on these boundaries at each one of these locations. So what can we do with that? How can we use this? And so what we can do is we can write a control volume, a conservation of mass, for just the left control volume. And that's going to be basically, well, we know the mass coming in at 1. And we can find a mass at 2, 3. That's kind of the mass leaving here. And that's the exit. And we know that the mass coming in here from conservation of mass, since this is a fixed grid, it's not getting bigger, our density is not changing. So we know that all of the mass coming in at 1 has to leave at this barrier, so this mass 2, 3. So we can use that information to perhaps write a relationship. So now we can write a relationship for this first cell, and we can say basically the mass in 1 minus the mass leaving is equal to 0. And then we can further kind of expand the algebra here, and we can, our mass flow rate, we can write it in terms of our density. This area A1 is going to be the area at this location. And this area A23 is going to be our area right here, and the velocity at this location. So now we kind of have a relationship that is based on the velocities, and these velocities are what we are interested in, but we're really kind of interested in determining the velocities at the centroid of each one of these locations. And so we have these interpolation techniques, so we can further expand this velocity 2, 3 using our interpolation technique. And now we have a final equation right here for this control volume right here that is solely dependent on the density, the areas at each one of these locations, and the cell centroidal velocities at each one of these locations. So now we have one equation now that is only written in terms of the values that we're looking for, the velocities, for one cell. So, and as you might speculate, we can do the same thing for this second cell 3, where we say the mass coming in at 2, 3, and the mass leaving at 3, 4 must equal 0. And we do the same expansion right here. And then we do, so now we have a velocity that's based on 2 interpolated velocities. So we do a bit of an expansion right here. And now we're left with another equation. It's a little bit longer equation and it involves the 3 velocities right here. The velocity at 4, 3, and you'll notice here this velocity 3 is weighted by 1 weighting value on the left-hand side, this 2, 3 weight, but it's also weighted by another weighting value, 3, 4, between here and here. So right here, here, and here. So it has a little bit different weighting value, but it's all written in terms of those. So now we have a relationship for our control volume 3. And now we're at control volume 4. And it's the same thing, and this looks very similar, kind of a mirror image of the control volume 2 of what it looks like. We have the mass entering here, the mass leaving here, and we get a very similar relationship. So now we have come up with, if we gather all these together, we have 3 conservation equations, one for each control volume. And now the system is really, the only thing that we have is the unknowns of the velocities at these locations. So we have kind of three equations, and can we break these three equations down to the point where we can solve them together and find a precise representation for the velocities at each one of the cell centroidal values. So let's just expand that a little bit, and let's just use a little bit of our engineering expertise here about what we know about this inlet. And so what we know about this inlet, and we kind of discussed this a little earlier, is we know the mass flow rate, we know the density in the area, so we actually know the velocity at this location, so it is a known value. So here we know a value right here. So that's very handy. So now we have kind of eliminated one of the unknowns in those three equations. So now we can use a little bit more, since from a system perspective, we know all of the mass that goes in 1 has to leave 5. And so we can kind of use the same reasoning there, and we know the mass coming in. And so now we have a precise representation of the velocity at 5. And so that's very handy. So now we've just eliminated another unknown. So we know the velocity at this location. So now we have just an unknown for 2, 3, and 4. So that is pretty handy, because now we're really kind of left with 3 equations and 3 unknowns. And if we do a little bit of algebra here, we can kind of break this down into some sort of matrix representation, where we have this larger matrix right here. We have 3 terms. So this V2, V3, and V4, those are our coefficients for these. And so we have a matrix. So we can kind of invert that matrix, because on the right-hand side, we know V1 and V5, and 0, that happens to be a 0 there, because we don't know. We had nothing in this equation that we could put on the right-hand side that we knew. And so now we can actually invert this matrix and solve very precisely for these velocities 2, 3, and 4. And so that's very handy. So now we have actually solved for the velocities at these 3 locations, and that's exactly what the CFD solver does. Is it builds up these relationships, it makes a matrix, and then it solves the matrix for the unknown values at the center of each one of these cells. And granted, if any industrial case that you run, this matrix is very large, which is one of the reasons why CFD tools take a lot of RAM in order to do their job. But the other thing that is very important to remember here is that this matrix right here is inherently dependent on these weighting values. And these weighting values are the choices that the CFD tool makes for the interpolation between each one of these locations. And so when you mine your CFD data, if you want to know what the face value is right here, if you're doing some sort of surface integral, you should, to be very precise, you should use the same weighting techniques that the CFD solver used in order to find your interpolated values at this location. Because typically the CFD tool itself, when all of the data is written out, it only writes out data at the centroid of each one of the cells, and then the face values on any exterior face. So this value 1 and 5 would also typically be written out and saved in your CFD tool. So that kind of gives us an overview, and hopefully that gives us a little bit better understanding of how our CFD tools use the control volume concept to build up and solve for quantities that represent conservation of mass. Another thing is like conservation of energy. You would find a temperature field that represents conservation of energy. There's no such thing as conservation of temperature. There's just conservation of energy, and then you search for a temperature field that represents conservation of energy. So I've kind of jumped ahead, and I did that discussion before this slide, but this is just reiterating these weighting values that we talked about before and the importance of post-processing. So now that we kind of have an idea of how these collocated data are determined, maybe let's just take a little bit closer look at the collocated CFD data. What is the form of the CFD data for conservation? These CFD algorithms, they work very hard to faithfully represent conservation of these equations. And we, again, we need to use methods that mine the CFD data in a way that maintains this precision. It's very important if you want to get precise numbers. So here is a kind of a collection of polyhedral cells here. And one of the nice things about the control volume technique is when you combine, you have conservation of mass of one cell, but you can actually add two groups of cells together, this cell and this cell, and those things also imply conservation of mass or whatever quantity you have. And those, so not only do you have conservation of mass, but on one, or you can have conservation of mass on even a subset of those. And here's kind of a picture of that where I've taken this grouping of cells here, and we have some that are kind of this magenta or purplish color, and then we have a brown color, and we've kind of broken this into two groupings of cells. And just to talk about, like, from a surface integral standpoint, if we want to know let's say, for instance, the mass that is passing from this group of cells into this group of cells, we would reconstruct the face values using those interpolation techniques for these blue dots right here. And you'll notice that these surface normals they're kind of in different directions. So we'll have to be careful about which direction the mass is going based on maybe a dot product of these surface integrals. But in general, if we do an integral through here, our conserved quantities, all of them, say for instance, mass that's leaving this group of cells must be the same that enters here, and vice versa. Any mass that happens to leave these cells must enter these. So that is one of the benefits of control volume techniques, is that you can kind of look on the inside of your mesh and still expect to get engineering representative values even on the internals, if you do integrations on the internals of your CFD predictions. So, and that kind of brings up another topic here, is surface integral weighting methods. How do you kind of group the values here? If we're going to find some sort of average value between, say, when you do an integration between these three, how do you weight the value between, the value you might have right here and the value you might have right here and the value you might have right here as some sort of average value for this group of faces? How do you weight those together is kind of the next question. So we're going to look at that, and we want to make sure that those, we've worked really hard to make sure that our data is very good on each individual cell, but when we do the integration techniques, we should also make sure that we're using these interpolation techniques that also honor whatever the physics that we're representing between each cell. So, and that really kind of talks about control volume methods, and I thought maybe we'd take a quick diversion here from that and talk about the evolution of control volume techniques over the years, and how we kind of got to this collocated representation that is widely used these days. And so we're going to start by talking about this, the original CFD tools that kind of evolved in the 1960s was introduced by Harlow and Welsh here. And they used these for solving fluid mechanics equations, but the primary variables were kind of stored at useful locations that minimized the interpolation errors. And they used a regular mesh structure here, and a regular mesh structure, we'll kind of look at some in a moment here, but they're basically kind of rows and columns. So all of the cells are little rectangles or cubes per se. And one of the reasons that they chose to use this meshing method was that there's this thing called a numerical pressure checkerboarding problem that it was a kind of a big problem if you wanted to store all of your values. If you're solving the momentum equation, you have pressure in there and you have conservation of mass and velocity, kind of need to store all of those at one location. You would like to, but what they found, if you do that, then you would end up with a pressure checkerboarding problem that made it numerically challenging. And I don't want to like dig into that. Well, suffice to say that they found that this staggered mesh style that they used kind of overcame that problem and allowed them to solve a coupled solution between the conservation of momentum and the conservation of mass. So now the example we started with, we just looked for a velocity field that was just representing conservation of mass. But we would like to, in the general aspect, we want to find a representation of a velocity field that not only conserves mass, but momentum, the inertia. That really needs to be taken into account. And another benefit of this, especially, the computers didn't have lots of RAM back then. So the linear system is quite easy to put together if you have all of your cells in rows and columns. It makes the indexing, it makes the organization of that data, and there are linear solvers that are quite adept at solving linear systems that are based on that kind of topology. So that was yet another benefit of this technique. So let's just take a quick look at this staggered mesh concept. And so really you kind of have, for two-dimensional, let's just look at a two-dimensional mesh here. And we have over on the left-hand side, we have control volume. And this is kind of the control volume that we have talked about to this point right now, where you have basically the centroidal value and is where your data is stored, and that's kind of where we found the velocity predictions in the example I did before. And that was where we kind of conserved mass. But what they found was that was challenging to do, and so what we really want to do is we want to pick a slightly different control volume for the conservation of momentum, and this control volume is shown by these green cells, and they're just kind of shifted to the right a little bit here, and they're staggered. This is kind of where the word staggering, and they're kind of staggered to the right here, and so the conservation of momentum is kind of shown and conserved on these cells that are kind of enclosed by these red lines. But it kind of has an advantage here. If you conserve mass for the velocities kind of going from left to right, you'll notice that where the centroid of each one of these cells, it's very close to the face of the area where you want to conserve mass. And that's kind of a convenient outcome of staggering the mesh here. And that has a lot of advantages. And then you can do the same thing for our Y momentum equation, where we have a staggered kind of in the up and down direction in the Y direction. And here the Y momentum is shown in kind of in this pinkish color, and the cell is represented by this green lines right here. And you can see once again, now we have the flow that's going maybe in and out in determining the mass at these locations. The centroids of each one of these staggered meshes for the momentum is right here, very close to where we would maybe want to conserve mass going in and out in the vertical location here. And so that has a lot of advantages, and it's kind of useful. So let's just talk a little bit about conservation of momentum. So in this particular case, if we want to conserve momentum, we need velocities at each one of these locations. And so we know we were going to have to use a kind of the linear or some sort of interpolation. Typically in these, they use a bilinear interpolation to get the face values in here. And here are some of the shown values of where the velocities would be here to find the values at each one of these locations, as well as the pressure, because you kind of need the pressure for each one of these locations. You'll notice right here the pressure was at the centroid of the cell, and that's convenient because now the pressure is right on the face where you would want to conserve momentum. And so that has some convenient aspects as well in terms of putting together a relationship that conserves momentum for the x direction. So that's another kind of a set of reasons why the staggered mesh topologies were chosen. So now the continuity and pressure solution is a little bit trickier. So the pressure can be viewed as really a response to the momentum. That's one of the other things about when you're solving the momentum equation. The momentum is really what you're conserving. And if your momentum changes, your pressure kind of has to respond to that. So the pressure, there's no such thing as conservation of pressure. It's just a field that has a pressure field that has responded to momentum. If you conserve momentum, you need something that kind of makes up the difference between the changes in the momentum, and that typically comes in as a pressure difference. The velocity field is known on control volume faces, and we kind of talked about that a little bit. And you'll notice here, it's almost there. And so depending on the person that developed the software, maybe they use a little bit of an interpolation techniques, but I'd say generally speaking, the fact that this is a little ways from this is generally said it's close enough for the things that we're doing, and the value at the centroid of the staggered mesh is typically used. And then when the other equations are typically solved, something like energy or turbulence quantities or mixture fractions, those types of things, in these particular techniques with the staggered mesh, those equations are typically conserved on the conservation of mass cells. So temperature would be at this location, your turbulence quantities or your mass fraction quantities would be stored right at these locations when the staggered mesh approach is being used. So, but the staggered grid does have some disadvantages. And one of the big ones is that if you're limited to rows and columns of cells, there are not many engineering objects, especially with the advent of all of the complex CAD tools that are available. You can make something very complex that it's kind of hard to find, a bunch of blocks inside there. So that is a big limitation in terms of representing complex geometry. So that is kind of an undesirable thing. The next thing is momentum. Here in this particular case, you'll notice that the momentum is conserved the x momentum is kind of conserved in one mesh topology. The y momentum is conserved in another mesh topology, but nothing is really conserved at one location. There's no conservation of momentum at one precise location. The momentum is kind of scattered around all of these different mesh topologies, and so there is some sort of inherent interpolation error if you really want to know precise momentum quantities or continuity quantities all at one location. It's kind of difficult to do with a staggered grid. And it also makes the organization of this data and the post-processing of this data a little more challenging because the data for the x velocity is at a different location than the data for the y velocity and the data of your temperature. So it makes the management and dealing with this data a little bit more challenging. So people are looking for ways to simplify that. And so that led to these collocated algorithms that are used on most tools these days. And this was really introduced by the work of Ri and Xiao in 1985. And this easily, one of the big advantages of these control volume techniques is it really made unstructured mesh topologies, including polyhedral meshes, something that is easy to develop software for. It reduces a spatial interpolation error. Here we're kind of using a one-sided velocity that conserves momentum here at the center of each one of the cells. So each centroid we have one self-centered velocity field that conserves momentum. But we really kind of have two pseudo velocity fields that we kind of pack around. A second velocity field here is kind of a filtered velocity field. It's kind of uses a very specialized interpolation technique between the self-centered values and the face values, and you come up with this face velocity that conserves mass. So we have this very specialized technique that gets us a face velocity that represents conservation of mass based on the centroidal values. So that is, it makes the velocity field a little bit more complex to deal with, but at least it is based on values at the centroid of each cell. And so this, of course, is one of the primary reasons is that the data is all at one geometric location. Now you have conservation of momentum and mass, and the conservation of momentum for each of the components, your x momentum, y momentum, z momentum, are all at precisely one location. So that has a lot of advantages. And that is, of course, why most CFD tools that are widely used these days, Azor, the CFD tool, ANSYS Fluent, Star CCM, OpenFOAM, these all kind of take advantage of this and use these techniques. But it does kind of increase, one of the main disadvantages of this, it really kind of increases the complexity of the momentum and continuity coupling algorithm. This algorithm becomes much more complex in terms of the implementation and stability in order to make it work very well. So that is one of the disadvantages. The other disadvantage is the complexity for post-processing tools, because you really have these two velocity fields. You have one velocity field at the centroid of the cell, and then you have this very complex interpolation technique that is not an interpolation technique that can be used by any post-processing tool like ParaView, for instance. If you import in the data from OpenFOAM into ParaView, it uses, there are a lot of very sophisticated interpolation techniques inside ParaView, but none of those interpolation techniques are aware of the interpolation methods that OpenFOAM is using, because OpenFOAM is using interpolation techniques that are based on the momentum equation solution and pressure distributions and things like that in order to do this sophisticated filtered interpolation technique. And those types of interpolation methods are not available within ParaView that I'm aware of. So you can get numbers that are close, but they'll never be as precise as, the tools like, so for instance, Azor, its post-processing tool is very aware of all of these nuances, and it can give you very precise numbers anywhere within your mesh and give you integrated values that are very precise and represent what you would expect from an engineering or scientific standpoint. Here's just another kind of quick look at this collocated data here, just to kind of reiterate how the collocated mesh works for the control volume method in the collocated standpoint. Here, I've kind of rotated the mesh a little bit here, and here at each one of these cell centers, that is our momentum conserving velocity field. These are all of the velocity fields. These face values right here, this is the mass flow rate, and that's typically what is stored by the CFD solver. When you save a CFD tool like ANSYS Fluent or OpenFOAM or whatever, they store some information or they reconstruct this information to get the mass flow rate on each one of these faces right here. So there's just a little bit more either storage or there's a little bit of information that needs to be reconstructed in order for the solver to do like a restart and start a simulation. So we kind of took a detour there to kind of look at a little bit of history between how the evolution Why do we have these collocated control methods? Where did we start? How did we get to where we are now? But let's go back and look at these surface integration techniques so that we can use this reconstructed face values for engineering tools. And I thought maybe we could look at some examples here about how you might go about doing that. And so here we have this surface integral, and here I talked a little bit before about we need to find each one of these values, and we want to find an average value of some quantity for all of these, faces between these two groupings of cells. And how do we find an average value there? And we need to use some sort of weighting method. And typically what would happen is you would take the weighting value. This phi would be some sort of value. So first, this phi value, you would have to use some sort of interpolation technique, which would be those W values that we used at the beginning to find a face value. So that would give us a face value at that location. And then you would weight that based on this value. And then you have a separate weighting value here, and a weighting value here, and a weighting value here. And so you sum up all of those weighting values, and then you divide, and that gives you an average value. And so you would hope that, for instance, the average value that you would get right here, if you're doing conservation of energy, it represents conservation, the temperature, for instance, that would be representative of conservation of energy, or velocity. If you found an average velocity here, what would be the velocity that would be the average velocity? So we need to make sure that this weighting technique, what are these weighting values? And these are methods, and you need to use different methods depending on the value that you're integrating. And it depends on the physics, it depends on that value. And most commercial CFD tools offer a number of different weighting techniques. And so the user is kind of left to make the choice themselves of whichever one is appropriate for you. And so it's good to know which one is appropriate so that you get numbers that are representative for what you are looking at. So let's look at that a little bit more. We want to make sure that this is tightly connected to the physics. We want to make sure that the method is consistent with the general control volume approach. Certainly, we've worked very hard to have each one of these individual control volumes, and the summation of each one of them also conserves mass. And so any integration technique we use should also represent what you would expect if you summed up a bunch of control volumes together. So let's just look at a simple example. And here I have chosen this T-junction example. And what we have here is we have the velocity on the left-hand side is being introduced here, and it's kind of going from left to right. And then we have another fluid that's kind of injected in a T-type way going down. And they meet in the middle here, and so we're kind of looking at the velocity field prediction right here. And this is a very coarse mesh. And you'll notice here each one of these blocks is colored by the value, the centered value here. So you can kind of see what these average techniques, or the average value in each one of these cells would be here. And the velocity vectors kind of represent the general directionality of the fluid as it passes through here. So you can see the velocity starts bending in this T-junction as it goes around here. This velocity tends to go downward as it goes through here, and then you end up with a little bit higher velocity down here. So we're going to look at this T-junction, and we're going to do some example surface integrals and see what we might get and how we would go about doing that. And we'll do it from an energy. We've kind of looked at mass flow rate before, but now we're going to look from an energy standpoint. How can we conserve mass? Energy. So here in this example, we're going to say that the velocity is the same on each one of these legs, but the temperature is a little bit different. So we have down on the left-hand side, we have our fluid, which is standard air, coming in at 300 degrees K on this side. And we have hot air coming in here at 600 degrees K or Kelvin. So that represents the temperature coming in. But how do we find out the amount of energy coming in here. And that means that we need some sort of way of converting temperature to energy, because energy is what the CFD solver is going to conserve. And so we have this enthalpy temperature relationship, a very common one. And so we're just going to pick something very simple. Since we're using a constant specific heat, we can multiply the specific heat times the temperature in Kelvin, and we can get an enthalpy value that represents the enthalpy. So the temperature here and the enthalpy here gives us an enthalpy value right here. And we can also find a mass flow relationship right here. And so we kind of need to sum that up. For the mass flow rate coming in right here, it would be the density at this location, the velocity at this location, and the area at this location. And then you would sum that up for all three of these cell faces right here, and we could find the mass flow rate at this location. And we could do the same here. And if you really I've put all of the numbers in here. If you care to go back and look at this, you can. This area right here is the area of each one of these faces. And of course, we've picked a very ideal, like the best mesh that you could possibly ever wish for here, completely cubic cells everywhere. And then, but what you have here on the right-hand side is three different temperature predictions and velocity predictions, and I've shown them here. Not only is the velocity different, but also the temperature is different, and what we would like to be able to do is get an integrated value here of what would the equivalent temperature be at this location. And if we were truly running a CFD simulation, we would never do this. This is just for an example purpose, because we would never want to run a CFD simulation to determine what the average temperature would be at this location, or the average velocity would be at this location. This is something you can get by just simply drawing your control volume around this whole system, and you could easily get those numbers. The CFD tool is not something you would use to get those values. The CFD tool is something that you would use if, say, you wanted to know the temperature in this area or the velocity that's in this area. And like I said before, the CFD tool allows us to peer inside the system, and the system is our overall CFD tool, but we want to peer inside it and get insight into what's happening inside that system. So now let's do a little bit of math here. So we're going to do conservation of energy here, and we can easily find conservation of energy. So we can find out the amount of energy that might be coming in at this surface right here. And so we can take the first three values here, which is the mass flow rate, which is the density, the velocity, and the area right here. And then over here, you have the specific heat times the temperature gives us our enthalpy. And so if you do all of the math there, you get this number 28,115, and that is a joules per second type number. And you can do the same thing, the same math up here. So now we have the total energy entering the system right here on both of these inlets. And we know from conservation of energy, since we have assumed that there's no energy leaving on any of the wall surfaces, the only way the energy can get out is on this right-hand side, so that we add this number with this number, we know this number right here. That is the total energy that has to leave. We also know from conservation of mass that all of the mass coming in at these two locations has to come out here. And so we know the whole mass flow rate. So we can easily divide the mass into this joules per second type number, and gives us this enthalpy relationship, which is a joules per kilogram type number. So now we actually know the enthalpy at this location. And so now that we know the enthalpy, we can use our relationship between enthalpy and temperature to get this temperature right here. And this temperature right here is the temperature that you would expect to measure there, that represents the conservation of energy of 450 degrees Kelvin. So we have found that value. But now, how can we get that value if we want to use our surface integration techniques? And so we can use our surface weighting method. And so I'm just going to tell you ahead of time, the appropriate weighting method is a weighting by mass flow rate. So we can use, so here, our weighting value, that W that we were looking at before, is the density for one of those cell faces, the velocity for one of those cell faces, the areas for one of those cell faces, and the temperature on one of those cell faces. Those are the exit values that we are looking at, divided by the total mass flow rate. If you go through and do the math, you end up with a value of on the order of 42 divided by 0.0933. And lo and behold, it comes out to be 450 degrees. So life is good. We're happy we're getting the same number that we would expect to get from a conservation of energy standpoint. But I thought maybe it'd be just kind of interesting to look at, well, there are a lot of choices in a CFD tool. What if we had chosen a different method? How different would the value be? And the commonly available weighting method is if you wanted to weight the values by area. And so if we just did the math for that here, and we said, here is the area of each one of those faces, we'll multiply it by the temperature on each one of those faces, divide by the total area, we can get another approximation of what the temperature would be. And it turns out that if you do that math, you get a temperature of 475 degrees. And so that is not physically realistic. And if you had used this method and actually went out and built this expecting to get a temperature of 475 degrees on the outlet, you would be disappointed because it doesn't really represent physically what would happen in this particular scenario. So hopefully this kind of demonstrates the importance of using the right values, because you always want to make sure when you're doing engineering, extracting engineering data from your CFD tool, that it always continues to honor these conservation of mass, conservation of energy type values, because we're engineers, we're scientists. We want to make sure that we are constantly honoring these types of, the things that we would expect. So this kind of concludes and summarizes what I have covered here. What we first started with is we kind of reviewed the fundamental aspects of what a control volume is, from a fluid flow standpoint. We discussed the connection of the control volume approach to CFD tools, analysis tools, based on these collocated data, storage techniques. We looked at a little bit of history about the staggered style solution methods for collocated methods. And then what we just discussed was this T-junction example, highlighting hopefully the importance of using the appropriate weighting techniques for getting precise values that continue to honor our conservation of, mass, momentum, all of the things that we would like to conserve. So if you're interested in more technical information, I enjoy kind of summarizing some of this, and so you could look here at azorcfd.com. There is technical information there if you're interested. There's also a YouTube channel that has additional information, technical content about CFD methods, predictions, and that type of thing. With that, I think that concludes my discussion. We'll see if anybody has any questions at this point.
Thank you so much, Jeff. Such an interesting discussion, and definitely some of the most forgotten or overlooked concepts in our day-to-day use of CFD. Most of the methods, as you said, employ the collocated mesh with the volume mesh approach, and then it's people don't really look back and how methods evolved from the staggered mesh approach and why wouldn't we use it again. But you highlighted some of these and talked about the use of memory channels or the use of memory storage. That's really interesting. Maybe I have a couple of questions. I also like that you used the T-junction example. As part of my PhD back then, I played a lot with this problem and verification and validation
Oh, good.
methods of the code implementation. That's an interesting problem.
Yep.
I have one question regarding just an open question. What would you say could be the future of the control volume method? Let's say with the emerging techniques, like almost daily techniques that come up with AI, or specifically speaking, let's say with the power of GPU coming now, accelerating like never before. Do you see that something can, let's say, something can take this method or replace it, or would it be just that the method can leverage the power of GPU now? Is it possible that you could port a code, let's say the solver part of the code from CPU to GPU, and use the current power of the GPU, or you would have to write the code from scratch? I would be very interested to know your opinion on this.
Okay, yeah, well, there's a lot to unpack there. So I would say, I mean, certainly there are people doing, there's no doubt people are rewriting their codes to run on GPUs, and that does require some restructuring to accommodate that type of hardware to take full advantage of the GPU, and there are no doubt people doing that and having some success in terms of increasing speed. Some of the limitations there, from what I understand, I'm no expert on this for sure, is that you're still somewhat memory limited. A lot of transient techniques are kind of leveraging that, and you're seeing the SPH methods and lattice-Boltzmann methods really benefit highly uh, from the GPU because they don't necessarily need to invert a matrix as heavily as like the steady state control volume techniques that are typically used by the traditional solvers that are a little more challenging to do on a GPU. So, but another thing that you had brought up was the AI and how AI might be using control volume techniques. And I was down at a NASA um, uh, group discussing these things with them. And one of the things that I thought was kind of interesting is they use, I think it's called PINs, but it's basically it's kind of a physics-based AI where they try to include some physics in the approximation and putting together these methods for fast techniques. And I would imagine since the control volume technique, we talked about the subsets of the mesh also conserve mass. And so it could provide a lot of information. The portions of a CFD tool, a CFD solution, portions of that also conserve quantities. And so AI could maybe leverage that to come up with, for particular cases, they could come up with very quick ways of approximating things based on looking at the CFD data for training purposes. So I do see that as a possible avenue, and perhaps people are already doing that to some extent.
Yeah, I think so, and I'm also very interested in what the future of CFD would bring us, in terms of tools or techniques. But yeah, looks quite interesting, but also sometimes too fast. Yeah. Well, let's see. Thank you so much again, Jeff, for your time and the interesting discussion, and I'm looking forward to more episodes with you. Thank you.